Hi, this is Dr. Matthew J. Traum again. This is the second of two videos from the first engineering design course lecture. This is the slide that we ended at, so hopefully now you're back from your break and ready to continue from here until the end of the presentation. So at this point, having digested the first half of the lecture, you're probably wondering to yourself, well, if design is more of a kind of a creative and artistic expression of getting from a set of customer needs to a final product and communicating that product to someone who's going to make it. Why in the heck did I take all of these really hard classes in the engineering curriculum, fluids and heat transfer and controls and thermo and manufacturing and vibrations and all those math classes and physics classes and so forth? Well, the reason for that is because a really important part of design is an analysis step. And the best engineers are people who have those basic fundamental skills from the engineering sciences and can meld and integrate them with the more creative and artistic aspects of creating a new product from scratch. And so this class is going to teach you how to meld those two skill sets together. So it's really important that you've taken those fundamental classes and you have that fundamental understanding. So, as I mentioned before, design is an iterative decision-making process, but it's a process where science, math, and engineering are all applied to essentially transform resources to meet a stated objective, and that objective, of course, is to meet the needs of the customer. Now, there is a really important step in the engineering design process, which is analysis, and so just to understand what analysis is, it's the gathering and evaluation of data and the reporting of results. So this is what you've done in all of your engineering science classes up until now. So the reason that analysis is important is because you want to take your final design and you want to analyze it to make sure that it is viable before you send your drawings down to the floor and somebody actually starts making this thing that you've designed. Because once you start making products, you can't go back and unmake them. You can't change something easily. So things that you might want to check include just component fitment. Do the different pieces of whatever artifact that you've designed actually fit together the way that you want them to? Another thing you might check is load analysis. Have you made this thing so heavy that it would crush itself under its own weight, for example? Or is it so heavy that someone who needs to use it can't actually move it? Another thing that we're, of course, interested in is cost. Have you made this thing out of gold, platinum, and silver so that it's so expensive that you couldn't possibly sell it at a profit? And, of course, there's many other things that you might want to check and pull from your arsenal of engineering science knowledge to do that. Then another piece here is this idea of solving design problems by breaking them up into smaller problems, so sub-problems. So this is another skill that we teach you in the engineering science courses. So we teach you to deal with complexity, and design is incredibly complex, and you might end up with a situation where as you broken up customer needs into sub-problems and you solve the individual sub-problems, you discover that the sub-problems are interconnected. So if you make one change to the design, it affects something else. And so you need that engineering science skill set in order to deal with the complexity of interconnected sub-problems. So that's how engineering design and engineering analysis are connected. And as I said, the reason that we do engineering analysis as part of the design process is because the cost of making a product change increases with the progression from the preliminary design to the final design. So we see this chart here where on the x-axis we have time, so preliminary design, detailed design, production, consumption, and then on the y-axis we have the cost that is required or that is incurred by making a change, and you can see this curve shoots upwards as we get farther in time. So the farther you are in the design process, the more expensive it becomes to make a change, and it turns out the greatest cost increase occurs between product production and product consumption. So that's essentially here between the production and the consumption. If you've already got something out on the market, and you need to recall it for some reason because you made a poor design decision, that is incredibly expensive. So we try to avoid making those really late changes in the design process to keep the costs down. This is just one example of a type of analysis that you're probably familiar with and you've seen before. This is just a finite element analysis of the structural rigidity of a convertible. And really this is just eye candy meant to show you one of the possible analysis techniques that you will draw from your engineering science background to apply to engineering design. So it's kind of neat to look at it wobbling back and forth there. All right. So this is the stepwise engineering design process. I'm not going to go into great detail here because this is just an introductory lecture, but we will be talking about these 11 steps, and you will actually be carrying out these 11 steps as part of your capstone design project. So I wanted to put it here so that you could reference it, so you could see it, and we are going to get back to this and cover it in great detail in future lectures. But here's the process itself, just so you can see it. Okay, now here's the fun part of the presentation. A little bit of discussion about good design versus bad design. Now, some people say, well, what is bad design? Well, you know it when you see it. What's good design? Well, you know it when you see it. And that for engineering is not really good enough. We like to have a quantitative description if possible, but at a minimum, at least a qualitative description of good versus bad design. So good design will meet all the technical requirements of the customer needs, whereas the bad design will only meet some of those requirements, or maybe even none of them. A good design will work all the time, where a bad design will work initially but will stop working after a short time, or if it's really bad, will not work at all. A good design comes in under the cost requirements. A bad design, cost overruns. Good design requires very little maintenance. Bad design requires frequent maintenance. Somebody's got to come out and fix the thing all the time. It's clearly a bad design. Good designs are safe. Bad designs are hazardous to their users. Good designs create no ethical dilemmas for the manufacturers or the users. Bad designs, unfortunately, raise some ethical questions and some ethical dilemmas. So that's at least a qualitative comparison between good designs and bad designs. Here is an example of a bad design. This is the push button that operates an elevator, and hopefully you can see the problem here is that there's a button here which might be associated with this arrow, or it might be associated with this arrow, and you don't really know. It depends on whether you read left to right or top to bottom. So it's not really clear whether this button sends the elevator up or down, or whether this elevator sends the button whether this button sends the elevator up or down. So this is a failure to think about the end user of this particular product and how they would interpret the placement of these buttons and the arrows. So that's pretty interesting. Here's another example of bad design. This is a cup filled with coffee. It's meant to be kind of a splatter shape, a cool shape, probably pretty difficult to manufacture this. And I will just describe this as a bad design because if you think about what happens if you actually try to take a sip out of this cup, you get a sense of what I'm talking about. There's almost nowhere you can put your mouth on this cup and take a sip where the fluid inside won't spill out onto your shirt. So that's another example of bad design. Here, by contrast, is an example of good design. This is by a colleague of mine, Dr. Amos Winter. He and I went to MIT together. This is the leveraged Freedom Chair. It's essentially a wheelchair that's designed for use in developing countries where there isn't a developed paved road infrastructure. And what's neat about this is it actually uses these long handles essentially as levers. So a person using the chair can either go really fast, or they can get a lot of leverage depending on where they place their hands on these bars as they use the bars to ratchet the wheels and move the wheelchair forward. So this is a cool design, an example of really good thought about how the end user would ultimately use this chair and what environment that user would use the chair in. And oh, I couldn't resist one more bad design. So this actually happened in a school district that was trying to um, uh, tell kids or help kids say no to drugs. So these are pencils, and the pencils were handed to the students with these words kind of engraved on them: "Too cool to do drugs," right? Which sends a great message. Again, this is a situation where the designers did not think about how the end users would ultimately use the pencils. So you stick them in a pencil sharpener, and the words start to disappear as the pencil gets used and becomes shorter and shorter. So first, it's the user is too cool to do drugs. Then, the user realizes that it's cool to do drugs, and then they just get the message, "Do drugs," and then at the end, they're just told, "Drugs." Whoa. So another example of bad design stemming from carelessness on the part of the designer to think about how the end user would actually use this product. But I think this one is pretty funny, so I put it in there at the end. Anyway, that concludes this presentation. Thank you for your attention, and we'll see you next time.